So thank you everyone who are still here, even though today is non-examinable. And also thank you for everyone who actually filled in the survey. So to let you know that your survey is not actually wasted, let me discuss a few things, a few of the findings with you. So the project. Okay, so the project is a large component of this module. And as you can see from the fact that people say that the project is killing me. The other thing is that we do have your textual feedback, right? One of the most common feedback is basically saying that the large part of the project is actually the non-examinable part, the coding for the front end, right? So yeah, that's the unfortunate side effect of this module. I cannot really do much about it. The only thing I can do is I've already started talking with Prof. Chan Chi-Yong. So even though it doesn't really affect you, it may help reduce the workload for the subsequent module. Okay? Yes. The other thing that we probably need to find out is whether or not you all know about the basic programming that we require. Right? For the web application itself, we gave out 2 starting guides. The first one is on Node.js stack, and the other one is on Python stack, the Python Flask. So we do get a lot of diverse people coming into this module, so we are not exactly sure what is your background and what is your preferred programming language. If you come from IS, the preferred programming language is likely to be Java, and Java has this actually have this JSP, the Java server. I forgot what's the P. Okay, so one thing that we can do is we can broaden the scope of the project to include basically anything. As long as you use a database, you can code in anything, even if it's just a text-based interface. Yeah, so that's one of the things that I was discussing with Prof. Chan. To be frank, the idea of a web application actually started from a long time ago. When I was still an undergrad, we also had to do this. Right, and to be completely honest with you, I didn't do my CS2102 project. So I did CS2102 together with CS2103 with the same group of people. So we had a deal because none of my teammates actually went for the CS2103 lecture. And the first prototype was actually very, very bad. So our deal was that I did all the CS2103 project, and then the rest of my group actually do the rest of the CS2102. Okay, so I didn't really know exactly how much work it is required for this module. Okay, so yeah, so that was the main part about this survey. Oh, this one is replicated. Yeah, and the other one is about the quiz. So there's a bifocal here. One says there is a good revision, and the other one is without the answer, I cannot benefit from it. Okay, there's 2 picks. So just for this week, I'm going to try to set up a quiz on Luminous. Okay, so that you can at least know that you did wrong. Okay, so that was my intention in the future, that I have this small set of quiz that you can try at the end of the lecture. So I'm probably going to try to start doing it now. One thing was that at the start of the semester, all of us lecturers were forced to use Luminous. So I'm not sure how stable Luminous is. I guess there's no escaping it. I couldn't find a suitable platform for this module to host on. I tried looking into cosmology, but again, as you know, cosmology doesn't really able to run SQL. And the other part of the problem is that, so I know that cosmology can run Python. So one of the things that I was trying in the middle of the semester was trying to find a good SQL interpreter that is written in Python. Because I know cosmology can run Python. If I can have an SQL interpreter run in Python, I can actually port everything to cosmology. Unfortunately, there wasn't really one. And I don't think I have enough time to actually even write a sufficiently good parser for SQL. SQL is a very, very permissive language where the case doesn't even matter. So it's a very difficult language to work with if you try to build a parser or an interpreter for it. Okay, so just for this week, I'm trying to get the quiz, and I'm trying to put as many contents to it as possible. Right, so you can try it out later. The other thing that I'm going to address was the remedial. This was the surprising, actually not exactly that surprising, but we had a very major problem here. We have an increased intake of students. I cannot even find a room. Some of the weeks I can't even find the room for the normal remedial. So just for this week, I actually booked 2 additional rooms. So I'm going to host 2 additional remedial, which is tomorrow and the day after tomorrow. From 3 to, I actually managed to book another time slot. So this one is wrong again. Okay, so there was one of the comments that I received that I managed to screw up a lot of the lecture notes. So this actually I just managed to book from 3 until 5. Okay, so I'm just going to be there at Programming Lab 4. I'm trying to get the standard one, the survey of what you want to get discussed there. But it will be better if you come up with questions during the remedial itself. Right? So 2 additional remedial session, which is on Wednesday and Thursday. It's a different room, which is the Programming Lab 4, the Com1B11. The room number that I get is Com1B11, but it's actually at the level B1, room 11. So if you follow the normal writing convention, it's supposed to be Com1, B1, 11. But for some weird reason, if it's a B1, they just put it as B. Okay? So those are the 3 components from the survey that I try to address for today. It's just to show that your feedback is actually being heard. Okay? Again, the announcement. So on the last week itself, week 13, we will have final demo of your project. It will be held during the normal tutorial time, as well as the Friday 3 to 6 p.m. So this is our standard slot for remedial. So it would mean that there will not be any remedial on Friday. The other unfortunate side effect is that I have to go to Japan on the 13th. So I cannot host the remedial in the first place. On Friday, the TA that will be doing the final demo will be Jinli. Okay, so she will be doing the final demo within 3 to 6. It will be a 15 minutes session, both for presentation and Q&A from us. You don't have to show everything. Show the most beautiful, the most complex, or whatever aspect it is that you are most proud of your system. There's a doodle for you to vote for your slot. It's a first come, first serve. So those of you who come now, you can actually try to get the earliest slot that you prefer. And for the last lecture on the 13th, on the week 13th, which is next week, it will be review, and again, it will be non-examinable. Okay? So today is also non-examinable. Assignment 3 plus midterm marks is partially out. I haven't excluded I've done the plagiarism analysis. I have some data. But there are also some students who emailed me the answer directly. So I haven't had a testing on those because the format was very, very different from the one I got from the Exemplify. And the last announcement for today is the assignment 4 reminder that you will need to download it by Friday, 11:50 p.m., even though you might want to do everything on Saturday, because the deadline itself is on Saturday, 11:59 p.m. And if you already know me, this is kind of not exactly the hard deadline, but the hard deadline will be on Sunday at, I think it's either 12:05 or 12:15 a.m. Okay, so I always put it at 11:59, and then I'll just put it at this time to account for the network delay. Okay, so I know a lot of you are going to try to do things at the last minute, so I will always try to account for some kind of network delay. Right, and afterwards, the website will be reopened on Sunday. Okay, this will be very, very useful if you want to check if your design, ER diagram, is compliance with the BCNF or 3NF or not. Okay, just you can try to test it there. Just make sure that you try to have a mapping. So the system that I have over here, we use a slightly different format from the one that we keep on using. For instance, when you specify your relations in the lecture or in whatever assignment you're doing, you need to have the attribute followed by a comma and then for another attribute. Okay? So this is what we've been using in the lecture and assignment. For the website itself, to make things simple, every attribute must be a single character. Right? And I actually forgot how I parse this, but it's best if you give every attribute as an uppercase. So what you should probably be doing is have your own mapping. Have a mapping like, let's say you have a password field map to a character B. Okay, so if you know your own mapping, then you can run it. You can run the algorithm on the website, assuming that the algorithm terminates. Then you get some kind of result, and then you can map it back. Okay? So yeah, so that's it for the announcement. For today, we're going to look at modern DBMS. So SQL, or the relational database, has been developed since the 60s by, I think, Edgar Cod. So you know the name Cod, he's the guy who created the BCNF together with Boyce. Okay, so Boyce Cod normal form. One of the guys is Edgar Cod. So in the modern DBMS, we have a few versions. The easiest way to modernize things is that, well, why don't we make it distributed? Okay, so this is the easiest, distributed and parallel DBMS. And then we look at another kind of DBMS, such as the OLAP, or online analytical processing. It uses slightly different mechanism, but one of the main improvement is on the multidimensional aggregation. It improves on multidimensional aggregation. Now, the latest trend are two things. One is the NoSQL and the new SQL. The major difference between them is that NoSQL came first, and the new SQL is kind of like the SQL answer to NoSQL. So remember that what sets SQL apart in the DBMS is that it has the ACID properties. Okay, so atomicity, consistency, integrity, and durability. Okay, NoSQL does not have that guarantees. New SQL tries to get the benefit of NoSQL with the ACID property. Okay? There are a lot of NoSQL database. We will look at one of them, which is the graph database. Okay? The graph database actually looks at data in the form of a graph, and the graph itself actually looks like your ER diagram. Okay? So it's kind of like an instantiation of an ER diagram. I recently read this book, which is about category theory. So category theory is how you categorize things. You start with a set becomes a category, and then you can do transformation between categories. One of the main things that struck me was that category theory says that category is actually isomorphic to database schema. Okay? So it's a kind of a very strong mathematical object. Your database schema is a very strong mathematical object. So what it also means is that whatever the NoSQL can do can actually be translated back into a kind of a database schema. Because graph is kind of a subcategory of category. There's a category called graph, right? So yeah. So let's look at distributed DBMS. So far, our logical view is that a single database is located at one location, let's say in your computer or your laptop, and then it handles all the workload, right? So that's your server. The distributed DBMS takes in a slightly different approach in the sense that your data itself is stored at multiple locations, and they can be spread far apart. So you have all this mini database. Okay, they're spread throughout the world, and it kind of follows your organizational structure. Okay, if your headquarters is in the US, but you open an Asia branch here, okay, so you can see that, well, most of the data for the Asia people will be stored over here. Okay, so not all the data are stored everywhere, but some of the data are stored in Asia, some of the data are stored in Europe, some of the data are stored in the HQ. Okay, and then we will look at how we can partition this data. Okay, so for instance, we can look at this thing called replication. Okay, so you look at the single table T. The question is, where does T located? Okay, so I have 3 marked location over here. Let's say we are only interested in this 3 location. If you look at the non-replicated design, it means that the entire table, one of the table, will be, all of it will be in one location. And it will not be available in other location. Okay? So think about your ER diagram. Let's say you have a user table. The user table will be located in Asia. Okay? And then let's say you're doing the student management project, and your student table is located in Europe. You can see how that can pose a problem because you need a foreign key constraint, which can cross the geographical boundary. Okay? A partially replicated means that some of the tables are available in multiple locations. Okay? So if you want to perform a kind of a join here, then it might be easier if the 2 tables are located in the same location. And then if one of the location actually breaks down, the database are not usable anymore, you have a backup. So if this location somehow breaks down, your entire system is still working because you have a backup copy, which is over here. So this gives a kind of a reliability, but at the cost of a complexity in updates. When you want to update a single data, a single row in T1, you have to update in 2 different locations, in 2 different geographical locations. Okay, and this can be very, very costly. The last one is that it's fully replicated. So everything is perfectly replicated everywhere. Okay, so updates is going to be very, very expensive because you have to update everywhere. Okay, so we have a few things that we can analyze here. One is that what is the advantage of doing this replication? Replication can give us, so like I said before, the advantage is that replication can give us reliability. In the case of fully replicated design, if location 1 breaks down, all the tables are not available, your system can still work. Okay? The other thing is that if one of the data is corrupted, so let's say this data is corrupted, you can recover that data by copying from the backup from the other locations. Okay, so there is a reliability here. The other advantage here is that there is a what we call a reduced network load. Okay, so imagine that you are a user in somewhere in Africa here. If the database is not replicated, so if the table is not replicated, if you want to make a query, you will have to send your data, let's say, to this the location number 3. Okay, and that takes a long time because of the geographical location, and we have a limitation in the speed of light. Okay, so it will take much longer than if you actually fully replicate the entire database and you want to connect to this. Okay, so that's the other advantage of replication. The third one is it has to do with join. Okay, so simpler transaction. So if you want to perform a join, let's say T1 cross product with T2. If T1 and T2 are located in the same location, then you can just perform the join locally and return the result. If, for instance, T1 is located at location 1, and T2 is located at location 3, and you are here, when you want to perform the join, the database has to communicate between these two. Okay, so either 3 sends the data over to 1, and then 1 computes the T1 cross T2. Or you do the other way. 1 sends to 3, and location 3 computes T1 cross T2. And then you get the data back from here. Okay, that costs a lot. Okay, especially if sending data over is not cheap, or if the data that you send over is very, very large. If your table consists of 1 billion records, then it's going to be very, very costly to send over the data. The disadvantage of using replication, as you can guess, is that you need to replicate. And to replicate, you need to increase storage. Okay? This will be very, very apparent if you have 1 billion records. If this one contains 1 billion records, you need 3 times if you want to duplicate it in 3 different locations, especially if it's a full replication. Okay? And again, like I said before, update is complex. Okay? And it's not that the single update is complex. The single update is costly on the network because you have to update on all locations. The complexity here comes from what happens if you have a concurrent update. Okay, so let me illustrate something slightly. With a simple example, you have full replication. You have one customer located in the US, one customer located in Africa. They do an update on the same row. So you do an update over here, you do an update over here. Okay? So now, what happens if both of these requests happen at exactly the same time? These two database, okay, to maintain the asset property, it has to lock down the table. It will have to say that, well, you cannot update this because I have a request that says that some people want to update this. Okay? So one of the update must fail if they want to update exactly the same row. Right? So you need a notion of what we call as a causality. You have two requests, let's say R1 here and R2. You need to be able to order them such that either R1 comes before R2 or R2 comes before R1. Okay? This is going to be complicated if we take relativity into account. So remember that we live in a physical world. In the physical world, Einstein discovered that there's this thing called the theory of relativity. Both of them can appear to be simultaneous, okay? In a sense that you do not know whether R1 comes before R2 or not. Okay? What you know is that based on this observer, let's say R2 comes before R1. Based on this observer, R1 comes before R2. So which one of these two perspectives is correct? Okay, so this is the major problem with any kind of distributed system. So it also affects the distributed database. So you need to be able to find a way to say that one of these comes before the other. Or, at the very least, you force that R1 comes before R2, even though, in reality, both of them are happening simultaneously based on the theory of relativity. All right? So that's some of the things that you need to take care of if you want to make a distributed system. If you want to know more, I'm not sure whether the higher level database module will cover this, but at the very least, there is this module called the distributed system, which is a level 5,000 modules. Okay? It used to be taught by Prof. Haifeng Yu, a very smart guy. I took that module under him, and I still don't really know what is happening in the class. Okay? So yeah, but he inspired me a lot. Okay, so that's the notion of replication. Okay? The other thing that we want to do is whether or not we need to fragment the data. So there's this notion called fragmentation. To make it simple, let me just illustrate to you what fragmentation means. You look at a table. You have T1, and these are all the data. You have T2. Actually, let's not look at the entire table. Let's just look at a single table, T1. You have the first attribute, the second attribute, the third attribute, and the fourth attribute. So what is fragmentation? Fragmentation means you want to split this data from one table, and where do you want to store them? So there are two ways to do this. One is that you have what is called as a horizontal fragmentation. In a horizontal fragmentation, the top component can be located at location 2. The bottom component can be located at location 1. Right? So that's a fragmentation. And why does it matter that we want to split it this way? Well, if you want to find an aggregate, like the sum of all things, then it's going to be difficult if you do a horizontal aggregation. Okay? If you want to sum this value, then you have to communicate between the two databases, at location 2 and at location 1. Okay, so then we look at the other kind of fragmentation that may help in this way. Well, what happens if we have a vertical fragmentation? So this 2, let's say it's located at 3, this 2 is located at 2. Okay? So now if you want to do aggregation on D, it's easy. All right? The problem with this is if you want to do projection. If you want to do projection and you want to project on B and C, and then there's a where clause, right? The where clause is that, well, it must be just only between these two. Then it does not make sense for you to split it this way. Okay, because on one hand, the database at location 3 doesn't know what is C, and on the other hand, the database at location 2 does not know what is attribute B. Okay? There is another problem is that because so far we haven't talked about functional dependencies. If there is a kind of functional dependencies that says that A is a super key, or A is a key, so you have A to B, C, D, well then if you split it up this way, then just knowing C and D does not make sense. Because how do you enforce this in the first place if you do not know what A is? Okay? So one of the requirements for vertical fragmentation is that every single fragment, okay, so this is another term that might get you confused with the decomposition because it's also called fragment. Each of these fragment over here, it must have the primary key of the table. Okay, so when you fragment this, the one at location 3, so let's call it T3, table 1 at location 3 here must have AB, okay, and table 1 at location 2 must have ACD. All right? And then again, if you want to perform a join, it will be hard. The other thing is if you want to perform projection, but the projection only involves one of the fragments, then it's very, very fast because you just need to ask one location. Okay? The other thing about this is that the horizontal fragmentation, there's one thing that I forgot to mention is that typically you do not separate this arbitrarily. You cannot say that the first 50 is at location B, the bottom 50 is at location 1. What you want to do is you want to speed up certain operations. Okay? And how do we do the speed up of certain operation that can actually make this to be split up naturally into these horizontal components? We did this before, and this is the splitting based on the where clause. Okay, so at the top, you can have some condition C. Let's say C, the condition C is going to be queried a lot. So you do the split, you do the fragmentation of the database based on this very particular condition C. If it satisfies C, you put it at location 2. If it does not satisfy C, you put it at location 1. So now if you do some kind of query that it must satisfy C, then you can just look at location 2. Okay, so that can be the advantage of the fragmentation. Okay, so that's the basic idea of fragmentation. So the non-fragmented will be something like this. It can have duplication or replication. But the table will not be split. If it's fragmented, then the table can be split. Okay, the superscript here is just some kind of fragmentation. It does not correspond to the location. So it will just have this table split into 3 parts. I don't care how it is split. It can be horizontal or it can be vertical fragmentation. But I have 3 different splitting. And then it will just store everywhere. Okay, typically what you want to do is you do not want these 2 fragments to overlap. But if it forces you to do the overlap, then it's possible, but it's harder. Again, the reason why we do not want to have overlap is because update is going to be difficult. Okay? So to prevent that overlapping is typically you have a certain condition C, and then the other one is you split based on not C. Okay? So then you can even split it further. So this is a very nice splitting because you split the 3. Right? So the usual kind of splitting, horizontal or vertical, you typically split it into 2 first, either vertically or horizontally. So let's say we look at horizontal splitting. You split based on the condition C, and then you recursively split it again. So based on this, you can have another condition, B, and this one is not B. Which again, you can have this B and not B. So now you can split into 4. Okay? And the condition over here is basically C and B. The condition over here is C and not B. And this one is not C and B. Okay, so here. And this one is not C and not B. Okay, so you have 4 different fragments split across the world. Okay? So now that we have fragmentation, we have replication, usually people do not do these 2 things independently. So what they do is they have a mix. You can mix and match any kind of replication and fragmentation scheme. Okay? So any questions on this? For any kind of distributed system that you have, there is an inherent problem with it. And let me show you what this very inherent problem is. We want to look at 3 particular properties. One is consistency. Okay? So we define consistency that every read receives the most recent write. Okay? Or you can give it an error. Okay? If you do not know whether this is the most recent write, you can just say an error. The second one is the availability. Now this one, you don't care whether it is the most recent one. You just want to have a non-error. Okay? If you combine consistency and availability, that means you must have the most recent write without an error. Now the last one is partition tolerance. What partition tolerance is, if you look at some location here, you do not know whether you have to connect to here, or connect to here. Okay, so it depends on which one you connect to. There will be a network delay. Or your message is getting dropped. Because if your connection is using UDP, there's no guarantee that it will always give a successful transmission. If it's TCP, then you know that it's guaranteed that it will be there. But you do not know when it will be there. It can be out of order, and so on. So what partition tolerance is that, let's say your message saying that compute this is traveling to this database number 2, and then suddenly database number 2 breaks down. Okay? So you do not know how the message is going to be dropped or how it's going to be delayed. What you want to know is whether or not there will finally be a response to this request. Okay, so that's what partition tolerance is. No matter how you partition it, the system must continue to operate. Unfortunately, right, as with any other thing in CS, there is this thing called the Brewer's theorem. Also known as the CAP theorem. CAP comes from the first 3 letters. So C, consistency, A, availability, and P is partition. It states that you can only achieve 2 out of 3. You cannot achieve everything. Right? But the good thing is that all of these notions of consistency, availability, and partition tolerance is very, very strong. You cannot achieve all these 3 in its strong form. What you can do is you can weaken them. Okay? So once you weaken them, then you can achieve a kind of a weaker consistency. One of the consistency that we typically look at is this thing called eventual consistency. Okay? Eventual consistency simply states that if you never perform an update to the database after some long time, arbitrarily long time, eventually all the database will be in a consistent state. Okay, so that's eventual consistency. You do not know when, but eventually after some arbitrarily long time, arbitrarily long but finite time, it will be consistent. Okay? So if you reduce the notion of consistency from the strongest form into this notion of eventual consistency, then yes, you can achieve all three. And that's basically what NoSQL is typically trying to achieve, a weak consistency called the eventual consistency. Okay? For certain scenario, this is not acceptable. For instance, imagine that you have a banking system. A wants to send $1,000 to B. At the same time, B wants to send $1,000 to A. Okay? If you are just saying that there's an eventual consistency, you may end up with a state that eventually, well, no, if you do not even have eventual consistency, you may have, or even if you have eventual consistency, you may actually arrive at the state that says that in this intermediate form, A actually has $1,000 more than what it's supposed to have. Okay, so I believe I did this simulation before when I talk about transaction. Okay? SQL does not have that problem because it has ACID properties. ACID properties, the C is consistency. It is consistent. But if you use a weaker notion of consistency, somewhere in the middle, you may have an inconsistent state. And if you keep on updating the system, because in banking you don't actually have the luxury of no updates, right? You have lots of transactions. So this inconsistent state will be just keep on propagating, and then you will basically just lose money. The other problem is that when you have a time sensitive database, like a movie theater or a flight booking system. If you say that in the middle, you have an inconsistent state that one seat is booked by two different people, even though in the end, eventually it will be a consistent state, but you have a very time-sensitive system that before the flight, you must have a consistent state. You cannot propagate the inconsistent state indefinitely. So any kind of time-sensitive system will need a stronger form of consistency. Okay? So unfortunately, the CAP theorem, or the Brewer's theorem, this allows us to have all these three. And this is kind of very apparent in a banking system because bank typically works across boundary. So you will need partition tolerance. You will need availability. Okay, so you must have a slightly weaker notion of consistency and probably a slightly weaker form of availability. Let's say you shut down everything at 10 p.m. GMT, just to make all the database consistent. So afterwards, it can be non-consistent. So yeah, so that's the distributed DBMS. This CAP theorem is actually proven by one of our lecturers in his PhD thesis. I believe his name is Professor Seth Gilbert. So if you want to know more about this, you can ask him about his thesis. Okay, so he's the one who proved the CAP theorem. But the last time I talked to him, he just said that, well, everybody knows the CAP theorem is kind of true, but nobody really wants to try the proof. So what he did is he labored through it to get the proof. Okay, he's a very humble person, but he's a very, very smart person. Right? So earlier I said that, well, this thing, 3 choose 2, is kind of like everything else that we have in CS. You may remember, or maybe if you haven't really done this thing, we do have this in the logic, we have this thing called undecidability. Okay? It stems from a notion that in the mathematical sense, when you have a theorem in a system that is strong, the strong system is kind of equates to a recursive system based on the Church-Turing thesis that says that every computation possible can be computed in a recursive system. You will encounter a statement a statement that is true but cannot be proven to be true. Okay? So that's the essence of undecidable. It was first proven by Gödel. It's the famous Gödel undecidability theorem. And if you try to read his original paper, it is very, very difficult to read. Okay? So I gave up. I just tried a simpler paper that tries to explain what Gödel incompleteness theorem is. Okay. But again, we have three choices. Okay? So the three choices are basically, so in the Gödel incompleteness theorem, we have three choices. One is that we want computability. And this kind of equates with a recursive system. Or even in its slightly weaker form, it's recursively enumerable system. Things like your piano arithmetic for natural number. And the other one is that we want to have consistency. This is a different notion of consistency. It is kind of like your Armstrong axiom consistency. It states that if a statement is proven to be true, it is a true statement. Okay? The last one is we want a system to be complete. Complete means that every true statement can be proven to be true. Now, what Gödel incompleteness theorem states is that if you start with a recursive system, okay, so you assume that it's a recursive system, and you assume that the system is consistent, the system will be incomplete. The essence of the Gödel incompleteness theorem is basically saying that he creates a statement that says this statement is false. Okay? This is exactly what he kind of, I mean, in essence, this is what he wrote, or rather a simpler variation of it. He says that this statement cannot be proven. Okay? So what does it mean to have a statement saying that this statement cannot be proven? Well, if your system is consistent, that means this one must be true. But if it's true, that means you cannot prove it. Okay, so it's incomplete. If you say that, well, I can prove this, that means the proof is false. It becomes inconsistent. Because what the statement says is that, well, this statement cannot be proven. Okay? So the brilliance of Gödel is that he basically creates this statement in a system that starts with a natural number. So piano arithmetic. Right? So again, we have the 3 choose 2. So a 3 choose 2 is kind of the main theme in mathematical logic. Right? And now that we talk about distributed DBMS, how do we try to scale down distributed DBMS such that we get the benefit of distributed DBMS without the disadvantage of distributed DBMS? Well, the answer is actually a parallel DBMS. A parallel system is basically you have several machines all located in the same location. It shares a single file system. So you have one consistent data that can be operated on by multiple machines. Okay? Network delays are not the problem here because you assume that the machine is closely located to the file system. Okay? So even if there's kind of a delay, the delay will be the delay in reading the file, and it's typically very, very small in comparison to the network delay. So yeah, so that's why I don't really talk much about parallel DBMS. The next interesting thing is this thing called the OLAP, the online analytical processing. To talk about OLAP, we need to first talk about what is called as a star schema. So in a graph theory, you have a node here. If it is connected to another node, and that node is the central node, this is what we call a star topology. Okay? Because it kind of looks like a star if I make it 5 like this. right? So this is a star schema. What it translates to is that you have this as one dimension of it, this one as another dimension, and this one as the third dimension. So it becomes like a three-dimensional data structure where each of the ID becomes the index for the dimension. So you can, so in this particular schema, you can get things like you can represent your data as a cube. It's a cube because you only have 3 dimensions. If you have more dimensions, then you have to talk in terms of hypercube. Okay, hypercube is a higher dimensional cube. A 2-dimensional cube is basically a square. A 1-dimensional cube is basically nothing. Okay, so when you talk about this, one of the dimension will be time. The other dimension will be location, and the other dimension will be product. Okay? So if you want to aggregate everything, this is what you will get. A single cube that contains the aggregation of all the data. Let's say you want to find the total sales. To find the total sales, you just say select sum sales from sales. Okay? So that sums up everything. However, if your table is very, very big, this is going to be a very expensive thing to compute. Now, what happens after you compute this, and then you want to narrow down? I've already computed the total sales. I want to narrow down that I want to find the total sales for each product, or let's say for a single product. So I'm narrowing down, right? If I want to narrow down, now I have to join with this. And then I need to group by. Okay? So I need to do the computation all over again. If I want to narrow it down further, for each product and for each time. Okay? So again, repeat the entire computation now with a join. So it is going to be very, very expensive to compute. And then I can do one more. Right? So what the dimensionality tries to do is basically it tries to compute this multidimensional aggregate. So let me show you an illustration of what this multidimensional aggregates is. So imagine that you want to first compute the total sales for each product and each time. You will get into this kind of data. Right? So let's say you want to narrow down into only one component, then you get this. Oh shit, the color is pretty bad. You basically get this. You basically get this one that is colored red. Okay? You get the sum from that particular part. Okay? So now if you have this, let's say you have already computed all of this. Let's say 1, 2, 3, 4, 5, 6, 7, 8, and the ninth one here. Let's say you have already computed this. If you want to compute the other sum, now it's easier. Okay? But if you want to narrow it down further, then you need to kind of split this up. Right? Because this part is an aggregate of things. So if you want to narrow it down, now you have to split it up into something like this. Okay? So what the online analytical processing system says is that in a business analytics system, typically you want to do this narrowing and widening a lot. Okay? You want to do this computation a lot. So what you do is you try to compute this cube or a hypercube if you want. So you want to compute this cube first such that if you then want to narrow it down further, you don't have to recompute everything. If you want to widen it, you just have to aggregate certain components. All right? So if you already have this partition cube, if you then want to compute the total sales, you just take everything, sum it up again. The sum from here, let's say 2, 3, 5, 9, 100, and so on, you just sum them up, and then you get the total sales. Okay, if you want to look at the other one, then you just have to shift your view over here. Okay, so the main thing is that if you can compute this cube, you're done. Okay, the hypercube is if you have more components, so let's say and something else, this is what a hypercube look like. Each of this becoming like a smaller cube. if you are more of a topological guy, from mathematics, a hypercube is, this is a cube. A hypercube is that, imagine that this box expand out, but because there's no out dimension, imagine that there is an out dimension. And then this one connects. This one connects here, this one connects here, this one connects here, this one connects here. Okay? This is the standard notion of one kind of projection of a hypercube. It basically, think of it like there's a cube within another cube. Okay, but again, this is actually a projection of a 4-dimensional hypercube into a 3-dimensional space. So it's not really an exact representation of a hypercube. We cannot create a hypercube in our 3-dimensional world. Right? But mathematically, you can always create a hypercube. So OLAP is kind of, I think it was developed in the 70s. We do actually have a small support for this kind of feature. If you want to do it, it's basically saying that you want to create a cube. Okay? So if you say that you want to create a cube, then it will basically just compute that hypercube in advance. Because again, every SQL statement is going to be compiled. So if you say that, well, this is one of the usage, then it will be pre-computed for you. All right? So again, none of this is actually examinable, so you don't really have to know all this. In fact, this is not going to be considered a complex query. Okay? I do not want you to use this in Postgre. Okay, so that's OLAP. The next part is about NoSQL. Okay? NoSQL is actually not saying that there is no SQL at all. It is actually not only SQL. If you use a NoSQL database, it typically supports SQL. Okay? The early NoSQL system is the Google's Bigtable, Amazon's Dynamo, and Yahoo's Peanuts. But from what I heard, because I'm not sure whether this anecdote is correct or not, but all those big companies typically start with a simple SQL. Okay? Google, Facebook, I believe they all start with MySQL. And then once the company grows bigger, then they decided to move to another things. Okay? So NoSQL typically tries to support distributed systems. Because once your company becomes very, very big, you want your data centers to be distributed everywhere. Relational database typically will not make it. So this is why we are still learning SQL, because it is simpler. At the heart of it, most startups will start with SQL. It is typically harder to set up your system if you start with a NoSQL. And by the time you kind of create your startup, you take a longer time to create a minimal viable product that a competitor will already encroach into your space. So most of the time, if time is of essence, you want to have the simplest system first until you encounter a roadblock. Okay? There are a few models to this. One is the key value. Key value is basically your dictionary or hash table. If I'm giving you this key, give me the rest of the value. Okay? You can think of it as if there's a functional dependency from key to value. Okay? So that's what a key-value pair is. There's a functional dependency from a key to value. The difference will be that the value can be of any type, the key can be of any type. Okay? The value can even be another key-value pair. Document is kind of like that also. So this is a document system. You create a document, and then you can narrow down further. If this ID is an order, this is the explanation for this particular order. This is the explanation for this particular customer. Right? And given this customer ID, you can even retrieve another document to explain what the customer is. Okay? So document is not relational database because a document can contain another document, contain a reference to another document. I tried this. You should not probably try. If you want, you can try this for fun. I tried to create a kind of similar system using relational database. So what I do is, if you can create a table for every user, because every user will have a username. Let's say uname, right? So what I did before was that I created a system where I have a table called t_uname. For any user that registered to my system, I will create a dedicated t_uname table for them. Then it kind of becomes like a non-relational database. So given a table with a uname here, this value is actually a kind of a pseudonym for another table, t_uname. So if this one is x, I get t_x table. Right? So it was something that I did for fun, but in the end, I didn't really find it useful. If you want to try it out, you can. The one that we want to focus more is this graph database. So I used to be in this research group called the graph research group. Okay, it's under Professor Stefan Bresson. He actually used to teach database, and most of the paper on the graph theory is now actually published in this conference called VLDB. VLDB is very large database. It's a very prestigious conference. It's top-ranked conference. So at that time, I didn't really know why. Like, what is the connection between database and graph? You can actually represent a database as a graph, and this is what we're going to discuss. I do also have a kind of a guide for you. So if you don't really understand SQL, you can try to do this. You can write a CV, right? If you don't understand SQL, then you can just write that you have an expertise in NoSQL. Okay? So that's what NoSQL. Okay, so yeah. So let's talk about this graph database system. There are a few things about graph. There's this thing called the property graph. The property graph, in the end, it will look something like your ER diagram, but each of the entity is unique. Okay? So if each of the entity becomes unique, so let's say instead of having a student enroll in a class, what you do is, well, there is this student. The student name is A, and there is this class, and then there's a connection between them. So this is CS2102. The student is enrolled in the class. All right? So the arrow implicitly becomes a relationship. Okay? But again, every arrow is unique. Every entity is unique because this entity is a student called A. So the student can also enroll in MA1506, which is a class. Okay? So another way to look at it is that it's kind of like an instantiation of an ER diagram. My undergrad FYP was on hypergraph. Okay, hypergraph is basically your functional dependency. Okay, hypergraph states that, so a normal graph, you have A here, you have an edge B. Okay, so you have a node, every edge connects two nodes. Okay, the outgoing, you have the outgoing edge and then you have the incoming edge. Okay, so but every edge connects exactly two nodes. A hypergraph is a generalization of this. What it does is that, well, you have A here, you have B here, you have what is called a hyperedge. The hyperedge may connect multiple nodes to multiple nodes. This is the direction. A graph traversal is basically saying that if I have visited A, I can visit B. Okay, so that's what a graph traversal is. A hypergraph traversal, there are a lot of different traversal. One of the most common traversal is basically if I have visited both A and B, I can now traverse this hypergraph to visit C and D simultaneously. Okay? Now, notice the similarity between this and functional dependencies. What this one states is basically there's a functional dependency, AB to CD. Okay? So, Armstrong axiom is basically just saying that you do a traversal. You do a complete traversal. Okay, because if from C you can go to E. Okay, so the Armstrong axiom states that the AB plus is basically everything you can visit from AB. Okay, so that's hypergraph. What we want to focus more is on the property graph because that seems to be the most popular. So the model first. Okay, so nodes represent an entities. It may have properties. It must have one label. It may have a properties. The label is basically becomes your entity set. The directed edge is a relationship. The label or the type here is your relationship set. Okay? And each property is a key value pair. So you can have this employee with this property. So the employee here is your label. This one is your properties. It's a key value pair. The name is Amy Peters. The date of birth is this. The employee ID is this. Okay? So let's look at one possible instantiation of a property graph data model. This was taken from or adapted from Robinson's, Weber, and Eifrom textbook, written in 2015. The way they write things is that the label is over here. Okay, there's a node, there's an entity of a label user. And the property it has is that it has a name. So for this particular node, the name is Jim. It has a label of user. Okay, Jim is a friend of Bob. And Bob is also a user. Okay, so this becomes a graph, right? It's a directed graph because the direction matters, and the label also matters. Now from here is actually not really it's not really a major stretch between this and a hypergraph, because a hypergraph can actually be represented as a and/or graph. Okay, so it's just some terminology. So if you want to know more, you can look at and/or graph. The interesting thing is, what can we actually ask from this particular graph? Okay, so for instance, if you want to ask who are all the friends of Bob, okay, so you look at one particular node. This is Bob, and then you kind of try to traverse everything. So the friend of Bob will be, well, this one is a friend of Bob, so this will be one of them. This is also a friend of Bob, so Jim is one of them. This is a friend of Bob, so Zach is one of them. Okay? So you can think of a query as if it is trying to figure out what is a subgraph within this graph that matches your property that you want. Okay? So it's basically a subgraph search. So this is what it will return if you try to find all the friends of Bob. So everything that is not highlighted will be ignored. In fact, Bob should be ignored, but Bob is your starting node, so it will be marked differently. Okay? Now, you can also kind of try to figure out, narrow down further from here, like all the friends of Bob who share similar friends. Okay? So, Zach is a friend of Jim. Jim is also friends of Zach. So, only two of them share the same friends as Bob. Yeah, this one is not. Okay, so Alice does not have any other friend besides Bob, so it does not share a common friend as Bob. Okay, so if you want to write this down, so if you want to write this down as a query, now your query have to look at the graph. You need to be able to describe the subgraph property that you want to look at. And one of the ways is to have this thing called the graph query language or cipher query language. What it states is that there is this Bob. Okay? So the property that you are interested in is that you have a Bob here, and there's a friend of. Okay, so this is a friend of. You don't care who they are called. They are called F here, and they are called E over here. Okay, you want to figure out, give me two friends of Bob, such that F here is also a friend of E. Okay, so this is what the cipher query language is doing. You want to find, embedded within your graph data model, this particular subgraph with this property. So once you have a matching on this subgraph, you then have an explicit instantiation of what F is. F will be instantiated to one particular F instantiated to one particular node, E is instantiated to one particular node. Then what you do is you can count how many of those are. You can collect the names. You can figure out what the name of F is. Okay, so this is how you write in a cipher query language. Okay, so let's try it one more. So again, this is non-examinable. I will not ask you to write something like this. Okay, so because imagine that we actually spent an entire lecture just to talk about SQL. Or in fact, we actually spent 2 or 3 lectures to talk about everything involving SQL. So definitely I'm not going to ask you about this. So let's try to find one more thing. For each user, you want to find the number of his or her direct or indirect friend. Now, direct friend is easy, right? If you want to just find a direct friend, then you just want to say that there is a node U, there is friends of with U2. And this is friends of. Okay? You want to find this embedding within all your data. Okay? The problem will be is if you want to find indirect friends. So as a notion, this star means is zero or more. Right? So fortunately for us, you cannot be a friend of yourself. So there will be no 1. Right? But there can be 0. Okay? So 0 may happen. So that's why this is optional match, because this one may not be matched with anything. Okay? Because you may not have any friend at all. In fact, we have a few people here without friends. Okay? So the star means that there must be a sequence of this. This one is nothing, 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 and then say U2. And all of this is friends of. Okay, I should probably not write it that way. You, friends of someone, friend of someone, and then friends of U2. Okay? So it's optional. It may not match anything, especially if the person does not have a friend. But you will definitely match you. Once you find a single user, okay, so this one is the label. If you don't put it as a label, then if you have multiple labels, then you will match everything. Okay? So you just want to find one single user first, and then you want to optionally match that this particular user that you found over here must have 0 or more friends. And then you want to match everything. All right? So that's what the property graph data model is. This is basically something that's kind of popular right now. This type of NoSQL is kind of popular. And so then let's look at what the future have for us. Okay, so in the future, now there's a kind of a attempt to compete with NoSQL, but without using NoSQL. So the competition is what we call a new SQL. It must have the ACID properties, as opposed to NoSQL, which have the weaker consistency of eventual consistency. New SQL must have ACID properties, but it must also satisfy the distributed system. And it's typically targeted at OLTP, so online transaction processing. So it's not just online analytical processing, it's online transaction processing. It features everything that you're comfortable with, which is the standard SQL, but it can run on a distributed cluster. Okay, so it's ACID. Okay, and again, because we reach a kind of a roadblock here because of the CAP theorem, so one of these must be sacrificed, or one of these must be weakened, so that we can achieve a kind of almost ACID. Right? Some of the examples is the clustrix. Okay, so these are just some of the examples. The thing about the OLTP is that unfortunately, 3NF and BCNF are not its target. So for OLTP, we can have this major problem with 3NF and BCNF. Remember that even with 3NF you can have redundancy. BCNF you don't have redundancy. Your consistency can be checked at each individual fragments. But the problem with those two is that the problem is exactly that you fragment the database. You fragment it a lot that if you want to get it back again, you want to get the overall data back again, you have to perform a natural join. Right? Natural join is expensive. If you have 1 billion data on one of the table, and then you have 1 billion data on one of the table, you potentially have 10 to the power of 18 data in the intermediate one. Okay? So join is very, very expensive. Most modern system typically does not try to achieve that decomposition up to BCNF or even 3NF. It even sometimes go into the lowest level of 1NF. What it means that you just put everything as a single table. As a single table, some of the data can be missing, so you can have null everywhere. It's fine. Okay? Because most of the time for an online transaction processing, you don't go far back in history. You typically want to just look at the latest trend. Right? What is the latest transaction? So someone just bought something, you want to just store it there. You know, it's just store it there. It doesn't matter how you store it. The fastest way to retrieve those information will be if they are in a flat table, 1NF. Okay? So sometimes you do not want to even go into decomposition at all. You just want to achieve a flat system. Okay? Especially if your table is very, very big. For instance, Google. Right? If Google wants to store all the information about all websites, there are trillions of websites out there. Okay, trillions might be overstating it, but at least there are billions of those, right? So if Google wants to decompose it, then the join operation will be very, very expensive. Now, if you do a Google search, then it might take a few minutes instead of a few milliseconds. And that is not going to be acceptable. The good thing is that most of the old data might not be relevant anymore. If a website is not frequently accessed, then it will just go behind in the history. That you don't even have to access it anymore. Okay? So in OLTP, you don't typically care about these normal forms. You don't care about decomposition. What you want is, how do I get all this data the fastest way possible? And the fastest way possible is if you don't even do a join, right? So yeah, but again, you trade the speed with the storage because you have a lot of redundancy. Okay? And in even future direction is that when you want to maintain a database, typically you need a dedicated database administrator. And we used to have this module, so I'm not sure whether we still have it anymore. We have a module just for database administrator, and typically it's a graduate level module. Most of this administrative function can actually be automated, and that's what database as a service is. Okay, so I'm giving you all this partition for free. So if you go to Amazon or like AWS, they kind of give you the partitioning for free sometimes. So if you want to say that I want this to be replicated across certain geographical location because I want to go into Europe market, I want this to be kind of replicated into a server there, Amazon will just do it for you. Google also will try to do it for you. Okay? Facebook, they use this service called Akamai. Akamai is exactly that replication service. Okay? So if you upload an image, the image may not even be stored at the Facebook HQ. It may just be stored at some Akamai local server. But there is a reference to the main database that if you want to search for this particular picture from another geographical location, just ask this guy. And then maybe that image is going to be transferred to another local server somewhere. Okay? So that replication service may have kind of a slight inconsistency, but in the case of Facebook, it doesn't really matter because the worst thing that can get is that you do not know what your friend is eating at lunch yesterday, right? So this kind of replication service can now be automated. So yeah, so that's what the newer version of things are. So you have a database as a service that you don't even have to care how the database is managed. So you can have all the advantage of all the new SQL, no SQL, distributed DBMS without actually knowing much about those. Okay? So yeah, so those are the modern DBMS. For next week, what we're going to look at is we're going to look at the review. I'm going to probably go through some of the past year paper and probably not the quizzes, but the assignments that we have. I'm going to, especially the later assignment, we're going to go through it slower. Okay? And again, it's completely optional. If you do not want to come, it's fine. There will be a webcast. But hopefully at least one or two of you are coming, so otherwise I will be giving lecture to an empty theater. Okay? So yeah, so thank you for coming today. So I'll see you next week.